Welcome to the Chemistry 1411 final exam review session. So let me go through a little bit of how this exam session is going to work. I do have a practice final exam here for us to use. However, I don't want to make you think that this is the only thing that you can ask questions from. I am actually going to open this up to you. If you have any questions from any practice exam that you might, or any former exam that you've gotten back from your professors that you'd like to go over, I am, of course, more than happy to go over any questions you have, regardless of where it comes from. Questions from the book, questions from your homework, anything you want to go over. This review session is for you guys and for whatever questions you might have from whatever source. So that said, I will now open it up to you. Would you like to just kind of go ahead and start at the beginning and go through as much as we can, or do you have some ideas on particular concepts and topics you'd actually like to go ahead and cover first?
I'm open to starting at the beginning and working my way through. I do have a question kind of on a problem we were working through in my class yesterday, but we can probably touch on it as we go through it anyways.
Okay, no problem. So looking at this first one, it says the law of constant composition. So you will likely get some definitional questions on your exam. And the law of constant composition basically states that no matter what a substance is, as long as it is a particular substance, it'll always have the same ratio of atoms, or same mass ratio. So law of constant composition applies to what? Solutions, mixtures, solids, or compounds? Yeah. Well, no, actually it's not. A homogeneous mixture can actually have any ratio whatsoever. Yeah, this is actually going to be a compound. So all a homogeneous mixture is a mixture where you can't actually see the difference between the different parts. So strictly speaking, apple juice is a homogeneous mixture. If you added water to the apple juice, it would still be a homogeneous mixture if you kind of stirred it up, because you wouldn't be able to tell the difference between one part and another part. So the composition is going to be different for any mixture, because mixtures aren't required to have a specific composition. However, for example, for like water to be water, you must always have 2 H's for every 1 oxygen. And so therefore the ratio of hydrogen to oxygen, whether it be the mass ratio or whether it be the atom ratio, will always be the same for a given compound. Does that make sense?
It does.
Okay, cool. So then let's go ahead and jump into number 2. It says gases and liquids share the property of what? Yeah, it's going to be the indefinite shape. So this is kind of like something that, I mean, even kind of told about the properties of gases, liquids, and solids since you were in elementary school probably. But yeah, solids have definite shape and definite volume. Gases or liquids have a definite volume but an indefinite shape. They'll kind of change their shape to mold the container they're in. And gases likewise will have an indefinite shape. They'll change their shape to mold the container they're in, but they also have indefinite volume. They'll expand in order to fill their container, whereas liquids don't. All right, so number 3, this is a temperature conversion problem. And this is one that these type of problems tend to give students a little bit of trouble. It says the temperature of blank Kelvin is the same as 63 degrees Fahrenheit. There is no direct conversion from Fahrenheit to Kelvin, but there is a conversion from Fahrenheit to Celsius. So the equation that relates Fahrenheit and Celsius is as follows. So essentially, degrees Celsius is equal to 5/9 times the degrees Fahrenheit minus 32. Now, of course, you can actually also, you can modify this, and you can actually rearrange this to solve for the Fahrenheit, which basically would be degrees Fahrenheit. I'd multiply both sides by 9/5, because if I want to cancel out a fraction, I multiply by the reciprocal. Now 9/5 times the degrees Celsius plus 32. So that's just a little bit of algebra, but this is your formula for solving for, if you want to solve for Fahrenheit or solve for Celsius. In this case, we're actually given Fahrenheit and we're asked to get Kelvin. And so we're going to actually have to use the top equation here. I have to use this top equation here because I need to get to Celsius before I can get to Kelvin. And so what I'll do here is I'll simply go ahead and plug in the appropriate information. 5/9 times the 63 degrees Fahrenheit minus 32. And if I calculate that, what do I get?
It's 17.2.
What'd you say?
17.2.
17.2?
Yeah.
Okay. That sounds about right. At 17.2 degrees Celsius. Very good. So that's obviously not going to be the final answer because that's the answer in Celsius, and Kelvin is going to be the degrees Celsius plus 273. And Kelvin is particularly important because it's the absolute temperature scale. And in chemistry, whenever we use temperature, we always use Kelvin. We actually never use Celsius unless it's a change in temperature. If it's a change in temperature, that's fine. We can use either Celsius or Kelvin because the change in temperature in Kelvin is the same as the change in temperature in Celsius. However, if we're going to use a temperature, say for example in like the ideal gas law, PV is equal to nRT, the temperature must always be in Kelvin. So 17 degrees Celsius plus 273, and one of our esteemed guests has already posted the answer. Thank you for that. 273. I can't write today. Let's try that again. There we go. 273. And that's going to be equal to 290 Kelvin. And 290 with a dot to be precise. But yeah, 290 Kelvin. So there we go. That's our answer. Now, if there's any of these that you're like, ah, gosh, I don't really know how to do this, it's a waste of time to go over this question, just let me know. We'll skip it. Now, what about the next one? How are your sig figs? How many sig figs should there be in the answer to the following question? Ah, yes, 4. Why should there be 4?
Well, so this one you kind of have to do the problem first and then count sig figs, but basically you get like 215.58, and the least amount of decimal points, or I'm sorry, least number of numbers to the right of the decimal point is 1 out of all of those numbers. So you just, yeah, you just round up, so it'd be 215.6.
Yeah. What did you say the full number was originally?
215.58.
215.58?
Yeah.
Yeah. Basically you have to round your answer to the place value of the largest uncertainty. The uncertainty is always in the last, is always in the significant figure furthest to the right. And so the uncertainty here is in the tenths place, here it's in the hundredths place, here it's in the tenths place, and here it's in the hundredths place. which uncertainty is larger, an uncertainty in the 10th place or an uncertainty in a 100th place?
The uncertainty in the 10th place.
Exactly. So your answer has to stop in the 10th place. So 215.6, and that would be 4 significant figures. Adding and subtracting, that rule for sig figs is one that a lot of students miss. So good job on that. Well done. What about the next one? There are 6 significant figures in the number blank. Okay, D? Yeah, it's going to be D. Trailing zeros are significant if there is a decimal point. And there is a decimal point here, so all those zeros are significant. Just out of curiosity, how many significant figures does this first one, does A, have? How many significant figures is that?
4.
Yeah, it's going to be 4. The leading zeros are never significant. Those are zeros before the first non-zero number. How many significant figures in B?
7.
7. Yeah, that one's pretty straightforward. Well, and what about C?
5.
Yeah, that's going to be 5. You guys are good at the sig fig stuff. That's good. All right. All atoms in a given element have the same what? So for atoms of the same element, so now we're at atomic theory. All atoms in a given element have the same what? B, yeah, the number of protons. They do not actually have the same density. And this is actually how you separate. This is actually how you separate nuclear isotopes. So one of the stories you sometimes hear in the news is a concern over the enrichment capabilities that the Iranians possess with regards to being able to enrich uranium to the point of being able to make nuclear weapons, which is about 35%. You get it to 35%, it starts to be like, or even 30%, that's nuclear weapons grade uranium. One of the ways in which you can enrich uranium is you use a really, really powerful centrifuge. But centrifuges that are powerful enough to separate isotopes based on density are extremely tricky to build because they have to be balanced perfectly or they will literally blow up and explode. So that's a tricky part about that technology. But effectively, in a centrifuge, you spin things around and items that are more dense will be drawn to the bottom of the centrifuge, where items that are less dense will tend to remain towards the top. You basically spin things around and create sort of an artificial gravity, and the centripetal force pulls the things that are more dense to the bottom. So this is a long way of basically saying that isotopes of isotopes of a particular atom do have a slightly different density because they still pack in the same way, because it's the electron shell that determines the size of the atoms, not the nucleus. Just as a point of reference, if the nucleus of an atom is the size of a basketball, then the atom itself, the full size of the atom with its electron cloud, is the size of Texas Stadium. So the nucleus the size of a basketball, the atom is the size of Texas Stadium. That should give you an idea of how big an atom is compared to the nucleus. The nucleus, which contains all of the weight, is actually an incredibly tiny area or tiny volume of the atom itself. It's a very small part of the atom itself. So the density is larger because the molar mass is larger of isotopes with more neutrons. Does that make sense?
Yeah, that makes sense for me.
Okay.
I kind of messed up there because I was only thinking about ions being the only difference in between them. I completely forgot about isotopes, so That was my fault.
And yeah, and I actually highlighted the wrong thing. I highlighted mass. I meant to say number of protons. So it's the number of protons that is the same. And actually the number of protons are actually also sometimes called the identity particle, because the protons are what determine what the atom is. If by some chance in a nuclear reaction you're able to change the number of protons, you actually change the element itself. That's nuclear transmutation. It changes into a completely different element. The protons indicate the element. Okay, so let's skip ahead to number 7. Which pair of elements below should be the most similar in chemical properties? Yeah, it's going to be strontium and barium, because things in the same column tend to have similar chemical properties. And for bonus points, why? Why do elements that are in the same column why do they have the same properties usually?
The valence electrons is what determines the properties.
Yeah, it has the same number of valence electrons, and essentially also effective nuclear charge is similar as well. Exactly. All right, so let's take a look at number 8. Elements in the group 7A are known as what? Yeah. Yep, that's right, halogens. B. All right, let's take a look at 9. There are blank protons, neutrons, and electrons in iodine 1- with a 131 charge. Do you want to take a stab at that? Or do you want me to kind of go through it?
I want to take a stab at it.
All right, go ahead. I've got some answers. Yeah. All right, so yeah, let's take a look at this. So if we look at the periodic table, we can see that iodine has an atomic number of 53. So if the atomic number is 53, that means the number of protons also must be 53. So therefore, only C and D are possible. The neutrons, if the mass of an atom is equal to the protons plus the neutrons. The mass of an atom, while electrons do have mass, the mass of an electron is so incredibly tiny compared to the mass of a proton or a neutron that we typically just ignore them. It's like weighing yourself on a scale. Oh, got that wrong. Weighing yourself on a scale. If you have a quarter in your pocket and you weigh yourself on a scale, and then you take the quarter out and then you weigh yourself on the scale again, are you going to notice a difference in the weight? Probably not, right? The quarter still has a weight though, right? It's not that it doesn't weigh anything, but compared to what you weighed, it's really not even noticeable. So yeah, protons plus neutrons is equal to the mass. So in this case, it's 131 is equal to 53 plus the neutrons. And then if you subtract 53 from both sides, that gives you 78. So very good. And just from that, you can probably assume that the answer is C. Now the reason the electrons are 54 is because in a neutral atom, the protons and electrons would be the same. But in an atom that has a charge, if there's more electrons, it's going to be negatively charged, more protons will be positively charged. Or in other words, if you want to use an equation, the protons are going to be, the charge is going to be equal to the protons minus the electrons. In this case, the charge is -1, so there must be one more electron. And since the protons are 53, the electrons have to be 54. All right, cool. So number 10. Predict the empirical formula of the ionic compound that forms between magnesium and fluorine. So one thing to note here is that any ionic compound is going to have an empirical formula. Oh, that's really fat. It's going to have an empirical formula that it's not going to have a molecular formula. And that's because ionic compounds don't form molecules. They form continuous crystal structures with no definitive beginning or end. The size of a quote-unquote molecule of a particular ionic compound is basically the size of the crystal, because the entire crystal is one giant network of the ions. Okay, so if we're looking at this, then what? It's like, yeah, somebody already put the answer. Yep, we have to figure out the ionic, the formula for the ionic compound based on the charges. And the charge of magnesium, if you look on your periodic table, is going to be a +2, and the charge of fluorine is a -1. And because the total amount of positive charge has to be equal to the total amount of negative charge, I'm going to be needing 2 fluorines to neutralize the 1 magnesium, and therefore my answer will be E. Okay, balancing equations. What is the coefficient of H2O when the equation is balanced? Do you want to go through this, or do you feel like you got a handle on this? Yeah, it would be 2. And essentially it's just about balancing it element by element. You can list out your elements. If you're somebody who's a little bit more shaky with balancing equations, or if the equation is a particularly challenging one, then you can just list out your elements C, A, H, and O, and list them out on both sides, and then balance it like that. However, if you're somebody, and then balance it one element at a time. However, if you are a person who has a pretty solid handle on this, you could probably balance this in your head without doing any fancy calculations. I can see over here on this side I have 4 hydrogens and I have 2 oxygens. And so I just balance it. Okay, so hydrogen needs to be balanced. There's 2 on one side, 4 on the other. I'm going to put a 2 here, and that's going to give me 4 hydrogens, 2 oxygens. It's now balanced. So that's a pretty easy one. And that's just going to be 2. Okay, now so which of the following are combination reactions? So here's distinguishing between types of reactions. Which of these would be a combination reaction? Combinations are also sometimes called synthesis reactions. Yeah, 2 and 3. And the way you can tell is a synthesis reaction always has one product. Anytime you only have one product, that's a synthesis reaction. It does not matter if it's elements or compounds. Anytime there's only one compound as your product, that's a synthesis reaction. Just out of curiosity, if you look at something like 4, which has PbCO3, there's only one reactant. What type of reaction would that be called?
Decomposition.
Yeah, it's a decomposition. And what about number 1? What would that be called?
Is that combustion?
Combustion, yeah. Hydrocarbon with oxygen, that's going to be a combustion, exactly. So, and there's also single replacement and double replacement. And, just in case, I'll go ahead and make a note of those. But a single replacement is something like when you have, for example, a compound, like silver nitrate, and you react that with an element, say, like copper. I'll even balance it because I'm just that kind of guy. So this is going to give you 2 silvers and copper nitrate, CuNO3 Basically, anytime you have an element reacting with a compound and you see that the ions switch places, sometimes it'll be you see the metals switch places or the non-metal switch places, that's typically going to be a single replacement. And then a double replacement is also called a metathesis reaction. That's anytime you have, that would be like if you had something like this, AgNO3 and sodium chloride. Anytime you have two ionic compounds where the ions switch places and you get two new ionic compounds, that's going to be single replacement. And the biggest difference between a single replacement and a double replacement reaction is that double replacements reactions are non-oxidative. So these double replacement or metathesis reactions, this is a double replacement, otherwise known as a metathesis reaction. Metathesis. Those do not involve oxidation and reduction. However, single replacement reactions are essentially almost always, I can't think of a case in which they're not oxidation reduction reactions. These are single replacement, it's one type of oxidation reduction reaction. Technically, synthesis reactions are most of the time oxidation reduction, and so are, combustion reactions are always oxidation reduction reactions. So yeah, the answer here is going to be B, 2 and 3. Okay. And forgive me if I'm giving you a little bit of extra information that's not related to the problem directly, because even though it's not related to the problem directly, there's a good chance that your professor could ask you the question in a different kind of way, and that would result in you needing to know some of this other information. All right, so take a look at number 13. This is an average atomic mass. How would you calculate the average atomic mass for an element like this?
Well, you just find the leftover percentage of whatever it is, and you multiply that by the weight. I think, right?
Not exactly.
Because you have the because if it's an isotope, they're obviously all the same element, right? So you can get the average of them, which is what the percent composition is referring to, I believe, is it's the average mass that's going to be found within a certain whatever.
Yeah,
man, I'm having a hard time reading that problem.
Yeah, and you may be expressing the right idea, but you might not be, or you might be thinking the right thing, but the way you're expressing it is a little bit imprecise. Basically, you have to take the weighted average, because notice that each of these masses has different amounts present. And we can't simply count all of the we can't weigh atoms individually. And we can't actually count up all the atoms or whatever and then take the mass of each one and then divide it by the total. So in this case, to deal with the incredibly large numbers of atoms that we have to do what's known as a weighted average. I think the easiest way to deal with this is this. So I would actually multiply each of my masses, 19, times the percent that it corresponds to. And then I'll multiply, and then I'll add that to the mass of the next one times its corresponding percent. And then I'll add that to the final mass times its corresponding percent. And this is actually, interestingly enough, this is how your professors actually calculate your grades. They do weighted averages. They say tests are worth 15%, right? Or they'll say tests are worth 25%, homework's worth 10%. Well, they'll take the percent and they'll multiply it times your average, your test average, and they'll take the percent for quizzes and multiply that by your quiz average. And then likewise. And then what they'll do is after they've done that, they will divide the total that they get from that by the total percent. In this case, the total percent should, in all cases, be 100. So I multiply the percent by the mass, which corresponds to it, and then I take that and I divide it by 100%. And that's going to actually give me the average atomic mass here, the weighted average. And what you should find here when you do that, what do you get? Yeah, should be A. Does that make sense? Cool. All right, so occasionally you'll be asked a question where it gives you the average atomic mass, and you actually have to solve for one of the individual masses or something like that. In a case like that, you can actually use the same formula to solve for it. If it's two isotopes, you might have to set the percentage of one of them as X, and the percentage of the other isotope will then be 100 minus X, 100% minus X. So watch out for those types of problems because professors like to give those. Now for mass percent of C in CH4, and like I said, if there at any point there's a problem you just want to go ahead and skip because you already know how to do it, you can just let me know. Something like this. Here's where my slightly OCD way of doing molar masses kind of comes in handy. I like to list out the elements, indicate how many atoms of each type I have, and then multiply the number of atoms times the molar mass. So in this case, the molar mass of carbon is 12.01, and the molar mass of hydrogen is roughly 1.01. So 4 times 1.01 is 4.04. Then I can add them together to get the total molar mass, which is 16.05. Now here's the thing. All I have to do here, and I can say this either as AMU or grams per mole. In this case, I'll just put AMU. To get the percent of carbon, I just take the mass attributable to carbon, which is the 12.01, and I divide that by the mass attributable to, or the mass for the entire compound rather, the part divided by the whole. And I times that by 100%. If I wanted the percent hydrogen, I'll just take the mass attributable to hydrogen, the 4.04, and divide it by 16.05 and multiply by 100%. In this case, this is clearly going to be about 75%. So there we go. Thank you. All right, how about 15? How many sulfur dioxide molecules are in 1.8 moles of sulfur dioxide? What would I do for this one?
You would first need to determine the formula for sulfur dioxide.
Actually, you would not.
Would you not?
In this case, so we're just going from moles to molecules, right? And what's the relationship from moles to molecules? Yeah, Avogadro.
Yeah.
Exactly. Now,
But
it's
if
not
you
a bad
didn't,
idea to know it's. Oh, go ahead.
oh, I'm
What were you
sorry.
gonna say?
I thought it said how many sulfur. I thought it was talking about how
Yeah.
many sulfur was in there. So that's my bad.
Yeah, if it said how many sulfur atoms
Right.
would you need then in 1.8 moles of sulfur dioxide, then you would need to. So
Yeah.
you're right.
My bad.
But yeah, in this case, yeah, no problem. So 1.8 moles of SO2, the formula for sulfur dioxide, is going to be, I'll just do 1 mole on the bottom. And then I use Avogadro's number, 6.022 times 10 to the 23rd. And if I look at these answers, I can see that my answer here is going to be, in all likelihood, D. And there we go. All right. Now this is a tricky one. This one is not easy. How many moles of germanium hydride are needed to form 8 moles of germanium trifluorohydride, according to the following reaction, if the product is obtained in a 92.6% yield? Now, we have to remember here that percent yield is the actual yield over the theoretical yield, right? So percent yield is the actual over the theoretical. Now, you can also keep in mind here that when it says percent, percent means per how many?
100.
Yeah, it's going to be per 100. So in this case, it's 92.6, and it's 92.6 actual over 100 theoretical. And 92.6 what? Well, the truth is, you can actually use grams or moles or whatever, because you're talking about the same compound. So if it's the same compound, then the mole ratio and the gram ratio will be the same. If it's different compounds, then you can't do that. But in this case, this percent yield is going to be the same compound because it's referring to the product. So in this case, it wants to know how many moles of GeH4 are needed to form 8 moles of GeFH according to the reaction. So they're needed to form this. So in other words, this amount here is what I actually need. But I'm going to have to figure out the number of moles based on the theoretical, because I'm going to have to put in a little bit more moles of GeH4 than would be expected because of the 92.6% yield. So I can actually go ahead and then start with my 8 moles of actual yield GeF3H. GeF3H. And then I'm going to convert the moles of GeF3H actual I'm going to convert that to moles of GeF3H theoretical. So this is the moles of GeF3H theoretical is going to tell me what do I need to shoot for. How many moles of product do I need to shoot for if I want to get that actual 8 moles? Or theoretical. Now, if I look at this ratio here, this is actually going to tell me what I need to do. I can put this down here. So my actual is going to be 92.6. Not 90.9. Actual is going to be 92.6. My theoretical is going to be 100. Notice whenever I'm using a conversion factor, the top has to equal the bottom. And this is actually, and I should emphasize the fact that this is the actual. Now, once I have this, I can convert the moles of G to moles of GeH4 that I'm looking for. And then I go ahead and use the mole ratio from the balanced equation, 4 to 1. And so what do I get for this answer? What do I get for this answer?
My calculator's not working as fast as I'd like it to.
That's okay.
I think it's like, I may have done something wrong, but I think it's like 2.15 moles of GeH4.
Yeah, you're absolutely right. So it's about 2.16, but yeah. So it's 2.16 moles. So the answer here is E. Now, how many of you think that if you had gone ahead and taken a shot at that on your own, that you would have been able to get the right answer?
No.
No.
So yeah, I mean, and that is a tricky one. Yeah. So reading the problems, being very careful that you look and analyze at what it is it's asking you and what it's given, is really essential here. It's very easy to kind of overlook the little details. Okay, cool. Let's jump ahead to 17. This is when aqueous solutions of AgNO3 and NaI are mixed, AgI precipitates. The balanced net ionic equation is what? What do you think?
Well, it can't be C, right? Because it's an aqueous product.
True.
Or D, or maybe D could be it. Actually, never mind.
So part of this question is about knowing definition. This is the net ionic equation, as opposed to the molecular equation. Yeah, Ethan, you totally hit it. It's yeah, A is the correct answer here. Which one of these would be the balanced molecular equation for this reaction?
Would it be either D or E?
Which one? D or E? Yeah, it'd be D because so E has sodium nitrate as the precipitate, but if you look at the description, it says silver iodide is the precipitate. So yeah, D would be the correct one. But yeah, in this case, the net ionic equation is going to be this. Very cool. All right, number 18 is the compound HClO4. What is that? Strong base, strong acid?
Acid.
Okay, is it strong or weak? Oh, we have some disagreements. Some say strong, some say weak. Now, unfortunately, this is just simply a matter of memorization. You actually have to memorize this. There are 7 strong acids, and this is one of them. C is the correct answer. So kudos to those lucky few who got that answer right. Do you want me to list out the 7 strong acids that you need to have memorized?
Yeah.
All right, let's go ahead and do that. I'll list them out real quick. So the 7 strong acids you need to know are the HCl, HBr, HI. Notice that HF is conspicuously absent. HF is not a strong acid. So HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. So these are your these are your 7 strong acids. Everything else is weak. There are literally millions, maybe more, weak acids. There's only 7 strong. So know the strong acids and you'll be in good shape.
Is HF not 1 because fluorine is so electronegative?
Yeah, so that's an interesting point, and I think that's one that I want to go into here. There are 2 different factors, and this will become also very important in organic chemistry. There are 2 different factors that really determine the strength of an acid. One is the electronegativity of the atom that it's bonded to, and the other, nice. So the professor made a song to remember the strong acids. One is the electronegativity of the atom that it's bonded to, and the other is the polarizability of the atom. And it turns out that the polarizability of the atom is more important than even the electronegativity of the atom. So, like for example, if you compare HF to HCl, HF is more electronegative. However, chlorine is more polarizable, and that's going to make chlorine a much more HCl a much stronger acid. So HBr is a stronger acid than HCl, and HI is actually a stronger acid than HBr or HCl, because the larger an atom is, the more polarizable it is. So that's just kind of a factor to keep in mind. Another one to keep in mind is that acids tend to be stronger when, for oxyacids, they tend to be stronger if they have more oxygens. So HNO3 is stronger than HNO2, which is stronger than HNO. And likewise, HClO3 is stronger than HClO2, which is stronger than HClO. Does that help?
Yeah, kind of. I'm still trying to wrap my brain around it, but it seems to make sense. I got the first part. The second part, I was still trying to catch up on it.
Basically, more oxygens in an oxyacid, the more acidic it is. All right, so now let's look at the following reactions. It says, consider the following reactions. Bum, bum, bum. What is the correct order of increasing activity for these metals? Now, when you talk about activity of metals, we're talking about the ease of oxidation. So a metal is considered more active because metals don't form negative charges, right? Metals
Correct.
do not form negative charges. Metals form positive charges. So a more reactive metal is one that more readily forms a positive charge. In other words, one that becomes oxidized more easily. So if I want to compare what happens here, I look here at silver, which has a +1 charge, and I look at zinc, which any element that's by itself is going to have no charge whatsoever. So what happens here? Which of these gets oxidized? Look on the product side, what's the charge of silver? Zero, right? Because it's an element by itself. What's the charge of zinc?
Two.
Would it?
Yeah, 2 plus.
2.
And also, that's part of those magic staircase of elements that you need to actually have their charges memorized. So most of the transition metals can have multiple charges. And those in the first 2 columns, they always have the same charge. First column always +1. Second column always +2, right? But there's a group of elements in the upper right-hand corner of the transition metal area that always has the same charge, and you need to know what they are. And so, for example, and there's a nice little staircase you can use to kind of identify them. So silver is a +1. If you locate silver on your periodic table, silver is a +1. And if I was to draw what it looks like, it's kind of like this. Here's your periodic table. Okay, so here is zinc, and below zinc is cadmium. And then over here is silver. And copper is above silver. Then you also have this, the periodic table pops up at this point, and you have aluminum here. And then you have gallium. And you have indium. Yes, I am that big of a nerd. I do have the periodic table nearly memorized. Yeah. So this little staircase of elements, the nice thing about this is that they have consistent, they have the same charge. They don't have multiple charges. And so they will not get a Roman numeral. If you see like zinc sulfide, it's not going to say zinc 2 sulfide. It's just going to say zinc sulfide because these don't have multiple charges. And you have to know what those charges are. And the charges for these are as follows. Silver is always a +1. Zinc is always a 2+. Cadmium likewise is always a 2+. And then aluminum and the two elements below it are 3+. So aluminum's a 3+, gallium's a 3+, and indium usually a 3+. So you have 3 plus 3s, 2 plus 2s, 1 plus 1. I call it the magic staircase. Okay, so going back to our equation, does anybody know what the definition of oxidation is? Probably, you may have to know it for the exam, so I thought I'd bring it up. What is oxidation?
A loss of electrons?
That is an accurate description of what happens in oxidation, but that's not why it's called oxidation, just like gain of electrons is not why it's called reduction, right?
Okay.
Because even though electrons are gained when reduction happens, when have you ever heard of reduction being called a gain?
Oh, we're talking about its charge then, right?
Yeah, exactly. So reduction is a decrease in charge. Oxidation is an increase in charge. Well, specifically, it's this increase in oxidation number. And oxidation number isn't always exactly the same thing as charge, but in many cases it is the same. So oxidation is an increase in oxidation number, increase in charge, and reduction is a decrease in oxidation number or a decrease in charge. So which of these elements is oxidized, silver or zinc?
I think it's silver. Oh.
So looking from reactant to product. No, it's okay. Looking from reactant to product. Silver goes from +1 to 0. Is that a decrease or an increase?
Decrease.
So therefore, it was
Oxidized.
nope. It was reduced.
It was reduced.
1 to 0, right?
It's
It
reduction.
went down.
Yeah.
Loss in charge.
0 to +2 is oxidized, right?
Yeah.
So zinc is oxidized, and I'm actually going to go ahead. So zinc is oxidized, and silver is reduced. Now the element that is more easily oxidized is the more active metal. So in this case, which one of these is more active, zinc or silver?
Zinc.
Yeah, zinc. Zinc is more easily oxidized. This is why it becomes oxidized by silver. So zinc's more easily oxidized, so zinc is more reactive than silver. So I'd say that zinc greater than silver. Or if I wanted to flip it around because it has these all facing the other way, I would say zinc is, silver is less than zinc. Okay? So now let's look at the next equation. I see that cobalt, and cobalt here Nitrate's a -1 charge, so cobalt here has a 2+ charge, and zinc has a 0 charge. No reaction occurs. Which one of these atoms is in an oxidized state?
Cobalt.
Cobalt, yeah. So if there's no reaction here, that means that cobalt is already in its oxidized state. It does not want to be oxidized by zinc. So therefore, it's likely going to be more active than zinc. So cobalt is more active than zinc. And then in the last one, I see that this reaction happens if I'm comparing silver, which is +1 over here, and it goes to 0 here, and cobalt, which is 0 here, and it goes to 2+ here. Which is more reactive, cobalt or zinc? I mean, cobalt or silver?
Cobalt.
Exactly. The cobalt is more reactive than silver. So putting those relationships together, which one of the 5 choices below best describes the order of activity in these metals? Yeah, A, very good. Because zinc or silver is less reactive than all of them, and zinc is less reactive than cobalt. Now there's also another easy way for these activity series. I wanted to show oxidation and reduction because you may be asked about oxidation and reduction and whether or not something's oxidized and reduced. But there's actually an easier way to identify the more active species. The less reactive metal will always want to be by itself. The less reactive metal will always want to be by itself without a charge. You can also think, if you can think of this in context of like people, a less social person will tend to always want to be by themselves, right? So a less socially active person wants to be by themselves. So the less reactive metal, the less socially active metal is going to want to be by itself as well. So if I look at these two, which one ends up by itself? Silver, because silver is less socially active. If I look at this one, which one ends up by itself? There's no reaction, so zinc. Zinc is less active than cobalt. I look at the final reaction. Which one of these ends up by itself? Look at the products. Silver. Silver is less active than cobalt. Does that make sense?
Yeah, that's very helpful.
Yeah, the less reactive element is always going to want to be by itself. All right, so let's skip ahead from there. Now, does anybody want to skip ahead to any particular thing? We've already gone about an hour, and obviously we're nowhere near done. We're not even quite halfway through. And I don't want to not get to questions you have, so if there's anything you want to skip ahead to, just please let me know, okay? Stop me at any point. Okay. So if there's thermochemistry, electronic theory, any of that other stuff, Lewis structures, please let me know. All right. Otherwise, I'm just going to keep going.
Can we be sure to hit rate of effusion? I don't know if we will in this study guide. I know it's in our the final exam study guide that we got from my class, but I don't know.
Yeah, no. Let's take a look and see if we can find Graham's law of effusion. So that's a gas law's equation. So let's see. Here's some SDP, ideal gas law, blah blah blah. Let's see if we can find Graham's law of effusion. We'll just make a question up. Yeah, no problem. And I will record the session for those who have to leave early or those who aren't able to attend. I'm recording the session. I'll be sending it out to you, so you'll be able to catch the rest of it. Okay. All right. So let's take a look at Graham's law of effusion. So basically, let's say you have a question like this, and I'm going to go actually just type up a question. How much faster will, or if it takes 10 minutes for a sample of hydrogen or helium gas to reach a detector from a jar containing a tiny hole, how much time would it take for a sample of chlorine gas to reach the detector in a similar or in the same apparatus? So Graham's law of effusion basically states that the root mean square speed is equal to the square root of 3RT over the molar mass. The root mean square speed of a gas is equal to 3RT over molar mass. So what happens is Graham's law of effusion takes this relationship and it divides it by itself in order to get relative rates. So it'll basically say that if I divide this expression by one similar to itself, what I end up getting is this. I get rate of gas 1 effusing over the rate of gas 2 effusing is going to be equal to the square root, because if I divide this expression, the first expression by itself, the 3RT cancels out, and I end up with square root of the molar mass of gas 2 over the molar mass of gas 1. So in this case, what I would do is I'd be like, okay, well, I know if I let's say I'm trying to figure out the speed at which it takes to get to a detector is directly proportional to the rate. So the rate of times, or the ratio of times, would be effectively equivalent to the ratio of rates here. So in terms of effusion. So what I can say is that if I call this the rate of helium, or actually just because I'm trying to figure out how much time it would take for chlorine, I'm actually going to switch this because I can actually decide which gas is on top and which is on bottom. It doesn't really matter. I could say RCl2 over RHE is equal to the square root of the molar mass of He over the molar mass of something else. No, just kidding. Cl2. Okay, so then I'm going to go ahead basically and plug in my numbers. Well, the RCl2 in this case, with the time effectively, is what I'm looking for, and I'll put in the rate of helium, which in this case is simply going to be the 10 minutes it took to effuse, right? 10 minutes, and reach the detector. And that's going to be equal to the square root of the molar mass of helium, which I think it's like 4.004. Correct me if I'm wrong. Over the molar mass of chlorine, and chlorine is 35.45 times 2, which is 70.90 roughly. Okay, so then all I have to do here is take the square root of oh shoot. I made a mistake. So this is not going to give you the right answer, and I'll tell you why. Because the rate, if you think of the rate of something, it's equal, rate is kind of like speed. So if I think about velocity, the rate of effusion, kind of a velocity, is equal to the distance divided by the time, right? So if I'm solving for the time here, the time is going to be equal to the distance divided by the rate. Okay? So time actually has an inverse relationship to the rate. So essentially, since the distance is the same here, what I'd actually end up having to do here is I'd have to say that the display, it would be the same distance divided by the time of CL2, which I don't know, over the same distance divided by the time of HE, which I do know, which is minutes. So the distance divided by the time, that's going to be the rate. So that's what I'm actually going to have to plug in here for this. So I'm actually going to go ahead and erase this and plug that in instead. Over distance divided by 10 minutes. And so what you're going to end up having happen here is that the distances, since it's the same, is going to cancel out, which is good because I didn't know it anyway. And then since I'm dividing by a fraction, it's going to flip to the top. And the new expression is going to be 10 minutes over the time it takes for CL is equal to this. And so at this point, you multiply both sides by TCL2 and then divide both sides by the square root of 4 over 70. And so basically, this is going to be TCL to the time it takes for CL2 to effuse is going to be 10 minutes divided by the square root of 4.04 divided by 70.9. Does that make sense? And the reason I caught that mistake is because if I had gone with that particular original setup, it would have taken less time for CL2. But see, here's the thing. Heavier gases always effuse more slowly because at the same temperature, the average kinetic energy is the same. But if the average kinetic energy is the same, that means heavier gases are moving more slowly than lighter gases. So in this case, 10 divided by the square root of 4.04 is 70.9. That's going to be about 42 minutes. So it's going to take roughly 42, if it took 10 minutes for the hydrogen to reach a detector, or for the helium to reach a detector, it would take about 4 times as long, 42 minutes. 42, strictly speaking, it'd be like 42.08, 42.1. I'm technically speaking, it'll be 2 sig figs because this is just 10 minutes, but yeah, 42 minutes. It would take 42 minutes for the chlorine to hit the detector. Now, it may only ask you a case where it says, well, how much faster? How many times faster is one versus the other? In which case, you can just do that ratio of rates, the RCl2 over RH2, and that'll tell you how much faster one is versus the other, or how much slower one is versus the other. But if it asks you for something like time, heaven forbid, they probably won't ask you that. But if they did, you'd have to do it like this. You may also just be asked a more theoretical question. According to Graham's law of effusion, which would effuse more slowly, hydrogen gas or chlorine? And if you look at the molar mass of chlorine, be like, well, that's a lot heavier, so that's going to effuse more slowly. Does that answer your question?
Yeah, I wasn't expecting all that, but yes.
Okay.
If I'm being honest. But yes, this is good.
Okay. And so Ethan also wanted to go over electron orbital or orbital diagrams, and whether it's paramagnetic or diamagnetic. A good question for that would be something like this. So it says, which electron configuration represents a violation of the Pauli exclusion principle? And the Pauli exclusion principle basically states that no two electrons can have the same set of 4 quantum numbers. So where do you see a violation of the Pauli exclusion principle?
Well, that's a good question. I know E is wrong. I know D is wrong, and C is wrong. But which one does the Pauli exclusion principle? I would assume, since in D, those two last electrons that were put are both going to have the same parallel spin, I guess. So they would both be like plus 1/2. And so that's would be my thought, since they're the same and they're both in the same orbital, they would have the same in value. So I guess D.
Yeah, well, B. So B is the B is the only one that has the 2 electrons that have the exact same spin in the same orbital. If you look at all of the other ones, as long as they're in different orbitals, they can have the same spin. But if they're in the same orbital, they must have different spins. Do you know
I
why?
didn't see that. Yeah, well, it makes sense because there's because of the forces that are acting on them inside the atom. They physically can't be spinning like that.
Well, in particular, it has to do with this. And you'll learn about a little bit more about this in physics. But basically, if I have an electron here, let's say it's spinning around this way, okay? An electron spinning in one way, like this, is going to generate a magnetic field in this direction, okay? If an electron is spinning the other way, counterclockwise, it's going to generate an electric field in this direction. And actually, I lied. I think I actually got those directions wrong because I was using my left hand. It's supposed to be the right hand rule. But basically, if they're spinning in opposite directions, they generate opposite magnetic fields. Well, what do you know about opposite magnetic fields? Do they attract or do they repel?
They attract.
They attract, just like opposite electrical fields. Well, an electron produces both an electric field and a magnetic field. The electric fields of electrons repel one another, don't they? Because they're both negatively charged. So the only way that they can occupy the same area is if they have something else attracting them, the magnetic field. So this is why electrons, if they're going to be in the same orbital, must have opposite spins. If they have the same spin, then they'll have the same magnetic field and electric field, and they'll be repelling one another and they'll fly apart. Does that make sense?
Yeah, that makes sense to me.
Yeah.
Cool. So now if we're looking at this, which one of these disobeys Hund's rule? Which one of these disobeys Hund's rule?
Well, C does, but so does D.
Does
And
D really disobey Hund's rule?
well, aren't they? Well, I guess maybe not. But I was thinking that they kind of had to go left to right, but maybe they don't.
Well, see, here's the thing. Hund's rule basically states, think of a Hund's rule like being at a party, okay? If you go to a party, are you going to eat half the cake before anybody else gets any? Especially if it's not your party.
No.
No.
Not if you're a polite person like Ethan, right? If you're a rude
Yes.
person, then maybe. So Hund's rule is basically the party foul rule. If you go to a party and there's cake, each person gets one slice of cake before anybody doubles up. Okay. So likewise, in Hund's rule, it's that each electron or each orbital gets orbitals of equal energy. Orbitals of equal energy, people of equal importance, get one slice of cake or one electron before any double up. Okay. So now for orbitals of unequal energy, the lowest energy orbitals have to get filled up first. So let's say this is a 1s, and this is a 2s, and this is a 2p, okay? Let's say this is a 2p. Okay, so 1s, 2s, 2p. Well, the lower energy orbitals have to get served first. So that would be like the birthday boy or birthday girl, and then like, maybe the family, okay? And then the friends, or something like that. But basically, you go from lowest energy orbital to higher energy orbitals. But for orbitals of equal energy, so the three 2p orbitals have equal energy. None of them is more important than the other. So when you fill those up, you have to put one in each before you double up. Okay? So let me ask you a question then. If I say that, then is this orbital any more important than this orbital, or are any of these orbitals more important than the other? Yes or no?
I wouldn't assume so, but maybe.
Yeah, no, they're not. They're all equal energy, so none is more important than the other. So it doesn't matter which order they fill up in there as long as each one gets one. What do you think? Does it matter if I start at the end and then work my way back, or start at the beginning and work my way forward?
No, I don't think it matters.
No, it doesn't. Yeah, it's completely random chance. So no one of those orbitals is preferred over the other. So it's a random chance which one gets an electron first. So D is actually a correct electron configuration that follows Hund's rule. So for Hund's rule, electrons fill degenerate orbitals. Degenerate is another name for orbitals of equal energy. Electrons fill degenerate orbitals singly before any orbital gets a second electron. And there's probably a better way to put that, but electrons fill degenerate orbitals singly before any orbital gets two. Okay. So now what about the Aufbau principle? Does anybody know what the Aufbau principle is?
I don't.
Okay, that's okay. You probably know what it is without knowing the name of it. But the Aufbau principle is lowest energy orbitals get filled first. The lowest energy orbitals get filled first. So which of these orbital diagrams violates the Aufbau principle?
E for sure.
E, yep, E is one of them.
A.
And A, yeah. E and A. The rest of them follow Aufbau principle, but E and A do violate it. Awesome. So you got your essential rules for electron configuration and orbital diagrams down now. Hund's rule, the Aufbau principle, and the Pauli exclusion principle. So I feel like I want to do something like with electron configuration.
So what are those big, there's those really big diagrams that they got a lot of boxes in them, and there's like dashed lines pointing to the center, and it's got a whole bunch of like
Orbital diagram?
SP and what would you call it?
It's an orbital diagram?
Is that what it is? It might, yeah, that might be it.
Yeah, it is that is an orbital diagram. I mean, are you talking about, I mean, you say dashed lines point to the center.
So we had a test question that asked us about, it listed a whole bunch of different, basically diatomic stuff. They weren't really, but it was like B2, and they were asking us, it listed a whole bunch of different elements that were the same element, but two of them, and they were asking us if they were, like, which one was paramagnetic and which one was diamagnetic, and they gave us a chart that we were supposed to fill in.
Yeah.
And
okay.
I don't know how to do that.
Honestly, it's actually okay. I know what you're talking about. You're talking about molecular orbital theory. That's an entirely different thing.
That's probably true, yeah.
If you're looking at specifically for a particular atom, anything that has unpaired electrons is called paramagnetic, which means it'll respond to a magnetic field. So if you look at these 5 diagrams, which of these would be paramagnetic?
E would be paramagnetic if it's truly correct.
Yep.
I guess
assuming
D
all
would be
of assuming all of them were correct, which ones would be paramagnetic?
E, D, and A.
E, D, and A. You only need one unpaired electron to be paramagnetic. However, which one of these would be diamagnetic then?
B and C.
B and C. Yeah, B and C would be diamagnetic because they're all paired. Now, typically, like you said, this is in the context of molecular orbital theory, right? And I don't think I have a question like that, but I can show you how to do it. So let's say, for example, I had the NO minus. Let's say I had the NO minus ion, okay? And then I had the NO plus ion. Which of these would be paramagnetic, or like what is going to be paramagnetic, which is going to be diamagnetic? Well, here's how you can figure it out. Okay, so what I can do here is I'd be like, okay, well, I'm going to do a molecular orbital diagram. On the one side, I'm going to have my nitrogen. On the other side, I'm going to have my oxygen. I'm going to write the electron configuration for nitrogen, which is 1s2, 2s2, 2p3. Okay. The electron config. This is the nitrogen. Just as a reference for you. The electron configuration for oxygen is going to be 1s2, 2s2, 2p4. Okay. So if I'm writing this, okay, so let's say I make the orbital diagram here. I have a 1s, I have a 2s, and I have a 2p. And on the other side, I have a 1s. I guess I could have stretched these out or drawn it closer to the top if I wanted to. A little too late now. That's good. That's fine. 2p. So if I filled this up, I realized that I could fill these up if I wanted to. Okay. If I wanted to, I could say, okay, well, this is going to be. This is not necessary for drawing the orbital diagram, but you could do this if you wanted to. I'm going to do it just because I think it might give you some insight on this. And then 4. And on the nitrogen, I have 1s2, I have a 2s2, and then I have a 3s2, or a 2p3 rather. But notice I also have a negative charge here. So I'm actually going to change the color, and I'm going to put a negatively charged extra electron in the nitrogen side, okay? So now I'm going to draw the hybrid molecular orbitals. So a 1s will hybridize into a sigma 1s bonding and a sigma 1s antibonding. The 2s is also going to hybridize into a sigma 2s bonding and a sigma 2s antibonding. The nitrogen is going to hybridize into the 2p is going to hybridize into a sigma 2p bonding Sorry, I know I'm drawing a little sloppy here. Sigma 2p and sigma or pi rather, two pi 2p bonding orbitals. 2 pi 2p antibonding orbitals. And a sigma 2p antibonding orbital. So when I do these hybridizations, I always get an equal number of bonding and antibonding orbitals, but they may not all be filled. So I'm actually going to go ahead and label these orbitals. So here's your sigma 1s. Here's your sigma 1s antibonding, usually with an asterisk is what they show it. Here's my sigma 2s and my sigma 2s antibonding, a little asterisk. And here is my sigma 2p bonding. Here's my pi 2p bonding. Here's my pi 2p antibonding, little asterisk. And here's my sigma 2p antibonding. Okay, does this make sense so far? So now what I'm going to do here is I'm going to pour all of the electrons that were in the original atomic orbitals into the molecular orbitals. So this is a reference though. The truth is I really could have ignored the 1s because they're not valence orbitals. And the valence orbitals are always going to be filled anyway, which means you're always going to get the cancellation of the effect of bonding and antibonding, because I have 4 electrons and I have to pour them in to here. So I have a filled bonding orbital and a filled antibonding orbital, which cancels out the bonding effect. So then the sigma 2s, I'll go ahead and put those in. I have 4 from the two 2s orbitals. And then I have a total of 8 electrons, 4 from the 2p orbital of oxygen and 4 from the 2p orbital of nitrogen with that negative charge. So then I'm going to fill in 8 here. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8. So because of Hund's rule, I have to fill up orbitals of equal energy singly before I do it doubly. So with the NO- ion, would that be paramagnetic or diamagnetic?
Oh, that would be paramagnetic.
Be paramagnetic because it is unpaired. And what would the bond order for this be?
I guess it would just be sigma pi pi.
No, bond order or BO, as I like to call it, is equal to the bonding electrons. So the bonding electrons minus the antibonding electrons divided by 2. Divided by 2. So how many bonding electrons do you have total in this structure? Count up all the electrons in bonding orbitals. Keep in mind we're focusing only on this part. We don't care about the atomic orbitals anymore because they're gone. They've hybridized.
Is it 8?
Actually, it's 10. Because I have 2 here, 2 here, 2 here, and 6 here, right?
Gotcha. Yeah.
So those are 10 bonding electrons. How many antibonding electrons do I have?
Is that 6?
Yep, 6. I got 2 here. Here's my 2 more anti, and then I have 2 here anti. So this would be 6. So 10 minus 6 divided by 2. The bond order of this would be
2.
Yep. So you could expect this molecule to be double bonded. Does that make
Oh, that's
sense?
so cool. That's awesome. I didn't know that. That's really neat.
Bond order corresponds with whether or not it's double bonded, single bonded, or triple bonded, or it is possible also to have bond orders of 1/2 or 3/2, so 1.5 bonds roughly. So if we look at NO plus, and just because I'm lazy and I really don't want to redraw this all, let's see. I don't know if I can copy this. I don't want to redraw it. I'm not going to redraw it. I'm just going to be lazy. If it was NO plus, let's say I change this to NO plus. If this was NO plus, that means I would not have that extra electron, right? Not only that, but I would also have 1 less electron, wouldn't I?
Yes.
And honestly, if I was looking at this, I'd be more likely to take it away from oxygen because nitrogen has a half-filled 2p orbital, which is more stable. And so I take it away from oxygen. Now they both have half-filled 2p orbitals. Now if I do that, now this is NO plus. NO plus has a total of 5 plus 6, which is 11, minus 1, 10 valence electrons. So that means if I pour those 10 valence electrons into the valence orbitals here, okay, I'm going to undo that. What did I do? Okay. All right, I'm just going to fix it. Okay, so if I just fill up these electrons, I would fill them up so the 1s orbitals fill like normal, 2s orbitals fill like normal. I have 6 between the 2p, so 2, and then this would be 3. Oh, well, actually, I put 1 in each. 1, 2, 3, 4, 5, and 6. That's 6 electrons that came from here, 6 electrons that came from there that get poured into these hybrid orbitals. Is this paramagnetic or diamagnetic?
It's diamagnetic. Wait,
It's diamagnetic. These are all paired? No. So NO minus and NO plus are very different. NO minus is paramagnetic, NO plus is diamagnetic. And NO plus has a bond order of what?
Zero. Wait, no, that's not right.
How many bonding electrons does it have?
6. Wait.
10 actually total. If you count them all up, including the 1s.
Oh, right.
Yeah, because I have 2 here, and I have 2 here, and I have 2 here, and I have 4 here. So that's a total of 2 plus 2 plus 2 plus 4, which is 10 bonding. And then as far as anti-bonding go, I'm going to put those in red. I have 2 here, and I have 2 here. So that's 4. So 10 minus 4 is?
6.
Divided by 2?
That's 3.
So this is a bond order of 3. Does that make sense?
It does. Does that mean it forms a triple bond?
It forms a triple bond.
Neat.
Yep, this would be a triple bonded substance. All right, cool. So let's go ahead and let me open it up to any other questions you have. Obviously, we don't have a ton of time left, but I do want to cover whatever else you might have questions over as far as possible. What should I hit next? Sorry for that singing in the background. My wife is teaching music lessons. And what else can I hit next? Thermochemistry, gas laws, molarity. What you got?
Well, if no one else is going to speak up, thermochemistry is certainly going to be, if I had to guess, that's probably going to be the worst one for most of us. So it might not hurt to go over some of that.
Okay, let's do it. Thermochemistry. Lots of fun with fire. Okay. So, so 23 and 24 are good examples of relatively simple questions you could be asked, which, if you're not prepared for them, you could end up getting wrong, and you'd be kicking yourself for it. So, number 23 says, what is the change of internal energy of the system that absorbs 2,500 joules of heat and does 6,755 joules of work in the surroundings? Here's where you have to know that the delta E internal energy equation, delta E is equal to Q plus W. By the way, this equation also corresponds to which law of thermodynamics?
Conservation of energy, which is the first one, maybe?
Yeah, the first law of thermodynamics. Okay, because they might ask you, which of the following expressions corresponds to the first law of thermodynamics? And they might show this one. You'd be like, what the heck? How is this conservation of energy? Well, it is because heat and work, they're basically saying the change in the internal energy of the system has to be, is dependent upon those two things, and therefore, basically the energy transferred in from the surroundings has to be equal to the value of Q, and energy transferred out in work must be equal to W or whatever. But anyway, the tricky part about this one is to identify which ones, or rather, whether or not these values are positive or negative. So in this case, generally speaking, when it gives you a question like this, notice it says of a system. So this is of the system, and so then all of these will be of the system as well. So what is the Q of the system?
That would be
About
positive 2,500 joules.
Positive 2,500 joules. So if heat is gained by the system, it's positive. If heat is released by the system, it's negative. In this case, it said it absorbs, so that's a gain, positive 2,500. What about W? This is a trickier one.
The work is done on the system, so negative 7655.
Yeah, the work is done on the surroundings by the system. So when you do work on, for example, your room, you lose energy, right? You spend energy to do that. If a system does work on the surroundings, it loses energy to the surroundings. So this is going to be negative 7,655 joules. And therefore the answer is C. Make sense?
Yeah, sounds
Yeah.
good to me.
All right, let's look at 24. Now, the next question requires you to recognize that when you're given the heat of a reaction like negative 790, that heat of reaction corresponds to the molar amounts of this. So what that's telling you is that when 2 moles of sulfur react with 3 moles of oxygen, you're going to get 2 moles of sulfur trioxide, and the change in enthalpy for that reaction of those amounts is going to be negative 790. As a result, you could actually use that as a conversion factor. So notice here it says the enthalpy change accompanying the reaction. If it said the amount of heat absorbed or the amount of heat released, you would only be able to put a positive number because there's no such thing as a negative amount of heat. Just like there's no such thing as a negative amount of people. There's no such thing as a negative amount of energy. There's no such thing as a negative amount of matter. However, there can be a negative change. So I can say that there is a negative change in the number of people attending this session. We started with 7 and now we're down to 4. So that's a change of negative 3. But there's no such thing as a negative person, such that if one person entered, there'd be 0 people in the session, right?
Right.
So because enthalpy change, positive or negative will be important here. It can be negative. So what I'm going to do is I'm going to say 0.95 grams of sulfur. And since I know that the equation is giving me the molar amounts here, these are moles, I'm going to have to convert the grams to moles. So grams of sulfur, moles of sulfur. So 2 moles of, rather, not 2. I don't use the coefficients here. When I'm converting grams to moles, what do I have to use?
Molar mass.
Molar mass from the periodic table. So this is going to be 32.065 or 32.066 depending upon the periodic table, but that's going to equal to 1 mole. Molar mass is always equal to 1 mole. So then I'll go ahead and put the next conversion, and here I can convert, now that I have moles of sulfur, I'll do moles of sulfur, and I can convert moles of sulfur to kilojoules using my delta H. So negative 790 kilojoules corresponds to the reaction of how many moles of sulfur?
2.
2.
2. Exactly. So then I just multiply everything on top, and I divide by everything on bottom. And if I do that, I get something. I don't know exactly what, but I get something. I think it might be negative 12, but I'm not sure.
Yeah, it's negative 11.7. So negative 12.
Which rounds to 12, yeah, because 2 sig figs to start, 2 sig figs to end, it'll be negative 12. Yeah, negative 12. Okay. So There we go. If you get a question like this, 72 grams of metal at 97 degrees is added to 100 grams of water at 25. Final temperature is 29.1. What is the heat capacity of the metal? This is actually a relatively tricky problem because you're adding two things. You're taking 72 grams of metal and you're adding it to 100 grams of water. And they have two different temperatures. Since heat is being exchanged between these two pieces, you can assume that heat is always going to be transferred from the hotter substance to the colder substance, right?
Right.
Right.
And because of that, you're going to go ahead and recognize that Q of the metal, the heat change of the metal, is going to have to be what?
Oh, negative Q of water.
Negative Q of the water. It's going to be the opposite sign because the metal's going to lose and the water's going to gain. But all of the heat gained by the water is going to be lost by the metal, right? And we're assuming here that there's no loss of heat to the surroundings. So this is where we recognize, well, each Q is equal to mc delta T, where C is the specific heat, delta T is a change in temperature. And so I can say, well, the mass of the metal times the specific heat of the metal, which is what I'm looking for, times the temperature change of the metal. Notice it says heat capacity, but it gives you the unit of specific heat. Specific heat is short for specific heat capacity. So it wants the specific heat capacity or the specific heat of the metal. And that's equal to the negative Q of the water, which is the mass of the water times the specific heat of the water, which is given, times the change in temperature of the water. Then all you have to do is rearrange this equation and solve for Cm. Now the only tricky part about this is the change in temperature. The final temperature of 29.1 is the final temperature of which thing, the metal or the water?
Isn't it both?
It's both. Exactly, it's both. So change is always final minus initial. The final temperature of the metal is 29.1. The initial temperature of the metal was 97. So the change in temperature of the metal is 29.1 minus 97.0. So it will be a negative change. And then on the other side, the change in temperature of the water is going to be 29.1, which is the final temperature of the water, minus 25.0, which is the initial temperature of the water. And so you're going to get, and then you just plug in the mass of the metal, which was 72. And the specific heat is what you don't know. I can just call that X. The negative mass of the water, which is 100. And the specific heat of the water, 4.184 joules per gram degree Celsius. And and then you just basically solve for X. Pretty easy at that point, right? So you can do that calculation.
Yeah, I think so.
You'll get what you get. I don't want to take the time to calculate that, but hopefully that will help you with regards to the thermochemistry stuff. Well, sadly, it looks like we've come to the end of our session. And what I would say is that if you have any further questions when you're going over this practice exam or any of the practice exams, because we actually have multiple practice final exams for this course. Please feel free to check some of those out. Actually, before I go, I'm going to close this, but let me share one other thing with you, because I want to show you where you can go to get some extra stuff, extra goodies, shall we say. I was like, okay, there we go. We're good. Okay. If you go to Google TCC SE Science, and then it'll pull up this page, you can then click on Chemistry Web Resources, which is up here. Scroll down to Chemistry 1411. Under Practice Tests, you will find a practice final exam for Dr. Chibuni's course, and also a comprehensive answer key. The practice final exam that we went over, which is this one, a practice final exam for one of our other professors. So 3 practice finals, yay. Let's say you're a little bit lost and you don't know exactly what to do here. If you're a little bit lost and you don't know exactly what to do, even with the answer keys, and you're like, this isn't really helping me, I don't know what to do, go to our video tutorial library, and we actually have a complete library of really great videos on every single concept. So if there's anything you're struggling with, it's all organized by chapter. Say you're struggling with something related to electron configuration, you can come over here, electron structure and quantum theory. And I think there's configuration, orbitals, quantum number, electron configuration, how to do electron configuration, how to do noble gas electron configuration, all of this other stuff, orbital diagrams, all that kind of stuff. So really great stuff here. Be sure to check that out. If you just want to have a quick reference guide around while you're studying and doing these practice finals, I recommend checking out our chapter reviews. Our chapter reviews have all of the our quick reference guides that basically summarize the entire chapter. And so it talks about, what are valence electrons, what are valence orbitals, what are the trends in the periodic table, there's ionization energy, electron affinity, etc. Those are going to be important. You're going to need to know those. Also, you have one here that includes electron configuration. If you just want a diagram of the periodic table, and how you would use the periodic table to do electron configuration, an explanation of how that works. Quick reference to our favorite little principles here, Aufbau, Huns, and Pauli exclusion. And some orbital diagram stuff too. So quick reference reviews to all of these different things, anything from molecular geometry to stoichiometry. So definitely, and polarity. So definitely feel free to check these out. Maybe have these on hand when you're working some of these practice problems. And of course, if you should need any further help from me or from any of the other, from a chemistry tutor, please come by and see us at the Science Learning Center. Actually, see us at the Science Learning Center. You'll see the SE Science Learning Center tutoring room. And if you click on that, you can join a session and you can get tutoring help from me or one of our other awesome chemistry tutors. Well, that pretty much concludes it. I wish you guys the best on, and girls, the best on your final exam. And thanks for coming.